Hello there, Mr. Sutton here, bringing you the AB Calculus 415 Extra Practice Number 1 solutions on advanced related rates. For this problem, we have fertilizer pouring from a chute at a rate of 14 cubic feet per minute, making a conical pile with an altitude that's always twice the radius. We want to know how fast the altitude of the pile is increasing at the instant when the pile is 12 feet high. And they're giving us the volume formula for a cone here. All right. So this is going to be a related rates problem. We have a rate of volume going on here, and we're asking about the rate at which altitude is changing. So we're going to write out a formula that ties it all together, like this volume formula for a cone, and we're going to differentiate with respect to time. But before we do that, you might notice that we don't have a whole lot of information on the radius. We don't have any numbers for the radius. We have what the radius is in terms of the height, but that's about it. So in order to make my life a little bit easier, I'm going to try to rewrite all of this in terms of just the height, since I've got a whole bunch of information about that, or at least I know what the height is at a certain time. So they told us that the altitude, the height, is always twice the radius. So we can write h equals 2r. And I'm just going to rearrange this and isolate r so that I can replace the r in the original equation with some h's. So if I just divide by 2, I have r is really the same as 1/2 h, or h over 2. So going back to my original here, I can substitute h over 2 for this r. And if I simplify things, so this is going to be h squared over 4. We have another h here, so that's going to be h cubed over 4. With a 3 out here, this is going to be 1 over 12 pi h cubed. All right, so this is what we're actually going to be differentiating, and you'll notice we don't have to worry about an r now. We also don't have to worry about a product rule, which also would have been kind of annoying. So taking the derivative with respect to time for everything, derivative of volume, that's going to be dv over dt. And over on the right side, using the power rule, we've got 3 times 1/12, which is 1/4, and we have a pi, and we have an h squared. And we also have a dh over dt because we just took the derivative of h, which is itself a function of time. So now we're going to go ahead and plug some things in. Now ultimately we wanted to know how fast the altitude was increasing. So that's dh over dt that we're solving for. So that means we must have values to plug in for dv over dt and also h. So going back to the dv over dt here, how fast is that going to be? Well, they said that fertilizer was pouring from the chute at a rate of 14 cubic feet per minute. So that's going to be 14 for the change in volume. And for the height at the exact time this problem takes place, that's going to be the 12 feet high that they gave us. So we're going to write equals 1/4 pi times 12 squared dh over dt. And at this point, we have a whole bunch of constants times dh over dt. So if we just divide both sides by all this stuff here, we ought to end up with our answer. So let me do that on the calculator. So here's what this looks like on my calculator. Because I'm dividing by a whole bunch of stuff that's being multiplied together, I'm going to use my fancy fraction mode in alpha y equals. Now let's see what this comes out to. So it looks about 0.124 if I round that off to 3 decimals. And what's the units going to be? Well, we're solving for the change in altitude, dh over dt. Altitude is measured in feet. Time is measured in minutes, so this is going to be feet per minute. So 0.124, and that's going to be feet per minute. There we go. And you could simplify this before dividing. Either way, that's what you end up with. For this one, we have oil spilled from a ruptured tanker spreading in a circle. The area of this circle increases at this constant rate of 6 square miles per hour. We want to know how fast the radius of the spill is increasing when the area is exactly 9 square miles. All right, so we've got a rate of change of the radius. We have a rate of change of area. So this is going to be a related rates problem. We basically have to set up an equation that ties all of this together and differentiate with respect to time. A good equation to use, because they didn't just give us one, is going to be the area formula for a circle. So that would be a equals pi r squared. And just taking the derivative with respect to time here, we've got derivative of a, which is going to be dA over dt. Derivative of pi r squared, that's going to be 2 pi r times dr over dt. So everything is a function of time here. And ultimately, I want to know how fast the radius is increasing. So I'm looking for dr over dt. That means I need to plug things in for dA over dt and also for r. So doing a quick check for information, rate of change of the area, they actually gave us that. They said the area was increasing at a rate of 6 miles per squared per hour. So we have something for dA over dt. R they did not give us, though. So we're actually going to have to go back to the original equation to get that, because they did give us the area. So if you know the area of a circle, you can work backwards to figure out the radius. We can just take this original equation and write 9 equals pi r squared. And then if we divide by pi and square root both sides, we can write r as the square root of 9 over pi. All right, so plugging everything in, we've got 6, that was my change in area, equals 2 pi times radical 9 over pi. And we still have that dr over dt hanging around because that's what we're solving for. Now I'm going to go ahead on the calculator and divide both sides by all this craziness next to dr over dt. Let me do that off camera. So here's what this looks like on my calculator. I used alpha y equals to get this fancy fraction mode because I'm multiplying stuff in the denominator, so I don't have to worry about using a parentheses or dividing over and over again. Pressing enter, this comes out to 0.564. Now, what are the units going to be on this? We're solving for dr over dt. Radius is measured in miles. Time is measured in hours. So this is going to be 0.564 miles per hour. On this one, altitude of a triangle is increasing at a certain rate, and the area is increasing at a different rate. So we already got more than one rate involved. It's probably a related rates problem. We want to know at what rate is the base of the triangle changing, given an altitude of 10 centimeters and an area of 100 square centimeters. All right, so what we're going to do here is basically set up an equation that ties all of these quantities together and then differentiate with respect to time. That's going to let us access these different rates of change that we're being given and being asked to find. So a good formula for this one, since we're talking about the area of a triangle, would be the triangle area formula. A equals 1/2 base times height. And I'm just going to go ahead and take the derivative of this thing with respect to time. So derivative of A, that's going to be dA over dt. A is a function of time. And we're going to have to do the same thing for B and H. But because these are two different functions, we're going to have to use the product rule. So let me set up the box and ribbon for those. For one of my factors, I've got 1/2 B. For the other one, I've got H. And the derivatives of those, we're going to have 1/2 dB over dt, because base is a function of time, and also dH over dt. H is a function of time. Using the ribbon to multiply those together, we have dA over dt equals 1/2 h dB over dt plus 1/2 b dH over dt. And at this point, it's time to plug things in and see what we're solving for. Now, they wanted to know at what rate is the base of the triangle changing. So ultimately, we're solving for this dB over dt part. So that means there's, let's see, 1, 2, 3, 4 things that we need to find values for in order to solve for dB over dt. All right, well, starting on the left here, dA over dt, that's the rate of change of the area. They said the area was increasing at a rate of 2 square centimeters per minute. So dA over dt can be substituted with 2. And then for h, well, they gave us the altitude. That's going to be 10 centimeters at this point in time. So this equals 1/2 times 10 times dB over dt, because we don't know that yet. That's what we're solving for. Now, how about the base of the triangle? Well, they didn't give us that, but we can work backwards to find it. We know the area of the triangle. We know the altitude, so we can use 1/2, or area equals 1/2 base times height, to solve for the base. We can write 100 equals 1/2 base times 10. And then working backwards here, let's see, divide both sides by 10. We have 10 equals 1/2 b multiplied by 2. We end up with b equals 20. So we're going to have plus 1/2 times 20. And dH over dt, that's the rate of change of the altitude. They told us up here the altitude was increasing at a rate of 1 centimeter per minute. So dH over dt is going to be 1. So there's that. And now let's just clean this up a little bit and solve for dB over dt. So we have 2 equals, let's see, this is going to be 5 plus 10. And if I subtract 10, that's negative 8. Negative 8 divided by 5 is going to be negative 1.6. And for the units, that's going to be, let's see, base is measured in centimeters, time is measured in minutes, so negative 1.6 centimeters per minute. On this problem, we have the base of a triangle increasing at a rate of 6 centimeters per minute, area is increasing at 9 centimeters squared per minute. We want the rate of change of the height of the triangle when the base is 8 and the area is 80. Okay, so this is going to be a related rates problem. We're given one rate of change, actually two rates of change, and we're being asked for another one. To get access to all those rates of change, we're going to have to set up a formula that relates all of these quantities and then take the derivative with respect to time, so everything is going to be a function of time. So a good formula to use here, since we're talking about triangle area, would be the area formula, A equals 1/2 base times height. And we're going to go ahead and just take the derivative here. So derivative of area with respect to time is just dA over dt. To take the derivative of the right side of the equation, I have to use the product rule. So here's my box and ribbon to help with that. So I've got 1/2 b, and I've got an h. And the derivatives, which will be 1/2 dB over dt and dH over dt. Using the ribbon to multiply that out, we've got 1/2 h dB over dt for one term there. And we also have plus 1/2 b dH over dt for the other term. Now ultimately, I want to know at what rate the height is changing. So that's dH over dt that I need to solve for. So that means I have to plug in things for 1, 2, 3, 4 other quantities. dA over dt, that's the rate the area is changing. They said that was 9 centimeters squared per minute, so we'll put 9 in there. H, that's the altitude. They didn't tell us that, so we're actually going to have to go back and solve for that. Now the good news is we know the area of the triangle and we know the base at this point in time. So if we plug those two quantities into the original function, the original equation, we can go backwards and solve for h. So I can write 80, the area, equals 1/2 times 8 times h. And then let's see here, this is really 80 equals 4h. Dividing by 4, we have h equals 20. So we can go back here now and write equals 1/2 times 20. And let's see, dB over dt, well, that's the rate of change for the base. They said base was increasing at a rate of 6, so there's 6. Plus 1/2 times the base, they said the base was 4, so 1/2 times 4. And dH over dt is just going to stay put because, hey, we're trying to solve for that. So at this point, it's just algebra. I'm going to clean things up a little bit here. So I've got, let's see, 1/2 of 20 is 10, times 6 is 60. Over here we have a 4 dH over dt. And let me just do the rest on the calculator, just so I don't mess it up. So we've got 9 minus 60. And I'll press equals, and then divide that by 4, giving me an answer of negative 12.75. Now for the units, the all-important units, dH over dt is what we're solving for. H, height, is measured in centimeters. Time is measured in minutes. So this is going to be negative 12.75 centimeters per minute. For this problem, we have a ladder 25 feet long leaning against the wall of a prison. Why it's leaning against the wall of a prison is anybody's guess. But the base of the ladder is pulled away from the wall at a rate of 2 feet per second. Sounds like someone's playing a joke on somebody. We want to know how fast is the top of the ladder moving down the wall when the base is 7 feet from the wall. Okay, so we have a rate of change for one dimension, and we're asked about the rate of change for another dimension. So this is going to be a related rates problem. We need to come up with a formula that relates everything and then differentiate with respect to time to get at these different rates of change. I'm going to start with a picture, though, just so I can visualize what's going on here. So I'm going to draw a triangle because that's what it looks like when you have a ladder leaning against a wall. It forms a triangle. And we have a constant value here. This is a 25-foot ladder. That is a fixed value. That's not going to change. What is changing is the distance between the ladder and the wall on the ground. I'm going to call that x. And also the distance between the top of the ladder and the ground, which I'm going to call y. And in terms of something that relates all these different quantities that are changing, at least the x and the y are changing, we can use our good old friend, the Pythagorean theorem, because presumably this wall meets the ground at a right angle. So we can say x squared plus y squared equals 25 squared. And this gives us a starting point that we can now differentiate and maybe solve for one of these rates of change. So taking the derivative with respect to time, derivative of x squared, that's going to be 2x dx over dt, because x is a function of time, plus we're going to have 2y dy over dt, y is also a function of time, equals derivative of 25 squared. Well, that's just a constant, so the derivative is going to be 0. And at this point, it's time to plug in some numbers and solve for the missing value. Now, what are we ultimately solving for? We want to know how fast the top of the ladder is moving down the wall. So we want the rate of change of y. That's what we're solving for, which means we need to know x dx over dt and y. So for x, well, we're already kind of running into trouble because we don't know. Well, actually, we do know that. They said the base is 7 feet from the wall. So we actually do know that x equals 7. But what we don't know is the y value. We don't know how high up the wall that ladder already is. So we're going to go back and actually solve for the y value. We know that at some point in time, this x equals 7. We want to know what y also equals at that point in time. So I'm just going to go back to my Pythagorean theorem. So we can write 7 squared plus y squared equals 25 squared. And I couldn't put that 7 in there in the beginning because that's kind of an instant value. It's not always true, but it's true at the time that I also want to figure out what y is. Isolating y, we can write y equals the square root of 25 squared minus 7 squared. And you can do that on the calculator if you want. I happen to remember that this is part of a 7, 24, 25 triangle, but you're certainly able to use the calculator on this particular problem. So one way or another, it does come out to 24. And then plugging everything back in, we said that the x value here at this point in time was 7. So we have 2 times 7. dx over dt, well, that's how fast the ladder is moving away from the wall. It's how fast x is growing as that ladder pulls away. They said that was a rate of 2 feet per second, so that's going to be a 2. And let's see, the y value we just found was 24, so we have 2 times 24 being added. And the dy over dt, we don't know what that is yet, so we're leaving that the way it is. All right, cleaning this up a little bit, we have 2 times 7 times 2. That's going to be 28. 2 times 24 is 48, and we have a dy over dt over there as well. And let me just do the rest on the calculator to get a decimal. So initially, I'm going to subtract 28. So I have a minus 28. And then I'm going to divide by this 48 coefficient. So dividing by 48. And that all is going to come out to negative 0.583 repeating. So negative 0.583. Now, what are the units going to be on this? We just solved for dy over dt. Y is measured in feet, and t is measured in seconds. So this is going to be negative 0.583 feet per second. On this problem, we have a boat being pulled toward a dock by rope attached to its bow through a pulley on the dock 7 feet above the bow. If the rope's hauled in at a rate of 4 feet per second, how fast is the boat approaching when 25 feet of rope is out? So this is a really tough one if you don't draw a picture to visualize it. What's going on here, just to draw a picture, this is a big triangle. We have a boat out here being pulled toward a dock, and there's a pulley that the rope is going through to pull the boat toward the dock. In terms of the measurements they've given us, let's see here. The distance between the boat and the dock, obviously that's changing because we're pulling the boat toward the dock. And the height of the pulley above the dock, that's going to be a constant. They said the pulley's 7 feet above the bow, which is also the dock's height. So we can put a constant 7 there. That's always going to be 7. And the distance between the pulley and the boat also is going to be changing, so I'm going to call that z. And we want to know if we're hauling in this rope at a rate of 4 feet per second, how fast is the boat approaching when 25 feet of rope is out? So none of these things are constants. These are all happening at a certain point in time. Since we have a rate of change and we're looking for another rate of change, the how fast the boat's approaching rate, this is going to be a related rates problem. We need to set up an equation that ties all of this together. No pun intended. Get it? Because there's a rope involved. But the equation that I'm going to use here is the Pythagorean theorem, because this sure looks like a right triangle kind of situation to me. So I'm going to write x squared plus 7 squared equals z squared. And I'm just going to go ahead and take the derivative with respect to time, because everything here is a function of time. So we've got derivative of x squared, which is 2x, dx over dt, because x is a function of time. Derivative of 7 squared is just 0, because 7 squared is a constant. Derivative of z squared is going to be 2z dz over dt, because this is also a function of time. And at this point, I have to figure out what I'm solving for and what I've got. So I want to know how fast the boat's approaching. That's this x down here. The dx over dt then is what we're solving for. So that means I better have something for x, z, and dz over dt. Well, what do I have already? The rope being hauled in at a rate of 4 feet per second. This is the rope right here, this hypotenuse. So I've got 25 feet of rope. That's this length. I've got 4 feet per second. That's how this thing is changing, and it's a negative number because the rope is being hauled in. Although I want to know how fast the boat is approaching, so, I mean, I guess two negatives could cancel each other out. But anyway, one thing I don't have is this x, and I need this x. So in order to find that, I'm going to go back to my Pythagorean theorem. I know that at this point in time, the hypotenuse of my triangle, this z value, this rope, is 25 feet. So I'm going to write x squared plus 7 squared equals 25 squared. And then if I square root 25 squared minus 7 squared, I'm going to get my x value, which is just going to end up being a 24, because this is a 7, 24, 25 triangle. But you could certainly do that on the calculator. So I can write 2 times 24 times dx over dt equals, and now this is going to be 2 times 25 for the length of the rope. And there's a few ways you could play this. So I'm going to write positive 4 for this, even though this dimension is decreasing, because they asked how fast is the boat approaching. So they want to know how fast we're moving in here. So that would seem to be like a positive rate of change. Anyway, putting this all together, we've got 48 over here. Over here, we've got 200. And if I go ahead and divide, I'm actually going to do this on the calculator. So here we go. 200 divided by 48 comes out to about 4.167. Now, what's the units going to be on this? I just solved for dx over dt. X is measured in feet, and t, time, that's measured in seconds. So this is going to be 4.167 feet per second. On this no calculator problem, we have the sides of a rectangle above increasing in a way such that dz over dt is 1, dx over dt equals, well, this is kind of interesting, 3 times dy over dt. And the instant when x is 4 and y is 3, we want to know the value of dx over dt. Well, all these rates of change imply that we're doing a related rates problem. So we need to start with an equation that ties all of these quantities together, differentiate with respect to time to get all these dt sort of fractions, and then we can solve for the dx over dt that we're looking for. So let me start with my equation. Since I've got a right triangle here, I'm going to go with the Pythagorean theorem. X squared plus y squared equals z squared. And now taking the derivative with respect to time, I've got 2x dx over dt, because x is a function of time, and so are the rest of these variables. We got plus 2y dy over dt, and this is going to equal 2z dz over dt. Going through now, what am I ultimately solving for? Eventually, I want to find dx over dt. So I better know what all these other things are then. So let's see here. We've got an x value. They said that was 4. dx over dt, we don't actually know, except that they told us that it was 3 times dy over dt. So I'm actually going to make that substitution right now, and hopefully that's going to pay off down the road. And then let's see, plus we need a y value. That's going to be 3, so 2 times 3. dy over dt, we don't know yet. However, if we figure out what dy over dt is by solving for it now, we could plug that in to this 3 times dy over dt and end up actually solving for the dx over dt that we were looking for all along. So we're going to keep going down this road. I think this is going to lead us to some happiness, but let's keep going. We need the z value and dz over dt. We have dz over dt, but we don't know the z value. Fortunately, we have an x and a y in a right triangle, so we can use Pythagorean theorem to get that third side. we can write 4 squared plus 3 squared equals z squared. So z is going to be the square root of 4 squared plus 3 squared. Well, square root of 16 and 9 is the square root of 25, which is just 5. And, I mean, you might have recognized this was a 3, 4, 5 right triangle anyway. So we're going to have this equaling 2 times 5 times 1. Again, 1 was our dz over dt. And we're going to have to solve this without a calculator now. So simplifying a little bit, I've got, let's see, this is 24 dy over dt. This is plus 6 dy over dt. And all of that equals 10. So then we can write 30 dy over dt equals 10. So then dy over dt equals 10 over 30, or 1/3. Now ultimately we wanted to find the value of dx over dt. So before you go ahead and pick A, that's not actually the number we wanted. We wanted to plug 1/3 in for dy over dt in this equation up here. So we're going to write dx over dt equals 3 times this 1/3, which actually comes out to 1. So that ends up being answer choice B.